Morning, everyone. Welcome back. Have you tried the homework? Any questions? Is it unclear anywhere?
Yes. Just one quick question. How much math should each problem take? I feel like I'm overcomplicating a lot of them and filling up pages, and I feel like I really shouldn't be.
You don't need to be, first of all, this is not a math class. We just use math as a tool, so you don't have to be so rigorous to prove every step. But for some of the, maybe some technical part, you just need to give an idea why it is true, but you need to show exactly why it's true. But for what we care more about, the claim of the statement, right? So, for example, we want to show, the first question is to show, I think in the first question we need to use Weierstrass theorem, right? And for that, to use that, you need to show the compactness, right? You need to show closeness and also boundedness. Closeness.
Yeah, that was another thing I was going to ask
that's
about.
Something you don't need to be so rigorous. So, for example, I think for closeness, you can just somehow just hand wave to show it's true. But what's more important is the boundedness. Just show why it's bounded. That's more important.
What I was going to ask about for that is the function proper? It doesn't say it in the problem, but if it's not
you
proper,
can assume it continues.
Yeah, you may assume. Yeah, for example, continuity is assumed in that problem. It's not clear there, but you can just assume continuity, and hence closeness is not a problem. So what's more important there is to show boundedness. Why the level set is bounded,
Right.
and then you can just apply Weierstrass theorem. So you just show the important part of the claim, but you don't need to be so worried about all the mathematical details. For some analysis part, you can just skip it and just say why it's true. Just give the reason, but you don't need to do a very detailed derivation or proof.
I also have a question about question 2. Like for the first one, you assume x0 is not inside Q.
Question 2 is about the projection.
Projection.
Uh-huh.
Yeah, and but if x0 is inside Q, projection is still the argument is still right.
Yeah, so because x0 is in the set, then it's a trivial part, right?
Yeah.
So we just care about the non-trivial part.
Okay.
Yeah. If you have more questions, just feel free to email me or come to the office hour. We have 2 office hours on Wednesday and also on Friday. Okay, so coming back to the lecture last time, we stopped at the last lemma about the localization idea. And so we just state the lemma again. We assume the function f is convex and also Lipschitz continuous. So it's Lipschitz continuous on a ball. So with that, we can say the difference between two function values at 2 points is bounded by the Lipschitz constant times some distance. And this Vf is defined over here. Remember, this has a geometric meaning. It's from the point x bar to the hyperplane going through the point x with the direction to be the subgradient. And this is, we are interested in the case where this is positive. We're interested in when this is positive, negative. And also, yes, it's condition is here. We are interested in all the point x such that this is really something that negative and bounded by r, so that it's in the ball. The point is in the ball. And also, so furthermore, what we can say is that suppose you give me a sequence of points from x0 to xk, and then if I pick the minimum point, the minimum one, the one with the minimum function value. So the difference between this minimum to the optimal value is bounded by m times vk star. Vk star is the minimum of all the vi's, and this also has another meaning. So suppose I have many hyperplanes, and this is h1, h2, h3. This value, so here is my point, x star. For my point x star, I have different vi's, right? v2, v1, v3. So this is the minimum among the 3. So it should be v3 here. And v3 is the radius of the maximum ball that is contained in this set S3. Right, the intersection of the 3 cutting plane half space is the localization site. So we are choosing, it's the minimum among the 3 VIs, but it's also the maximum radius of a ball in the set. Where's the laser?
Would you please explain the DLF one more time?
The geometric meaning?
Yes.
It's given by this formula. From this formula, you can show, because, for example, this one is to normalize the direction. And this is the, so this is the point x, and suppose this is the direction. This is x bar. So this is the so the point x bar is here, and this vector x minus x bar is this vector, right? So you can put it here. And so this is the inner product of this vector with this unit vector, right? And that's the projection onto it, so it's the distance. Okay, now let's prove this lemma. Let's consider the point xp bar. This is a projection. Oh, I shouldn't erase it. This is the projection of this point x bar. Projection onto it. So it's x bar with projection. This point is, of course, in the cutting plane, in the hyperplane, hx. And also we can say that because of the subgradient inequality, right? This is just zero. They are perpendicular to each other. And also we have, so if f is, just as the assumption said, if f is Lipschitz continuous on the ball, right? If f, so the first inequality here is by this one, f of xp bar is above f of x. And the second one is due to the Lipschitz continuity of the function f. And the last one is because this is actually exactly equal to the last one. Because this distance exactly what we have is defining, right? It's the distance from here to this hyperplane. So with this, we prove the first one. So, and also you can apply this inequality to with x to be xi and x bar to be x star. For x star, this is always positive. This is always positive. So we have this inequality just by applying the one above. This is defined to be Vi, and hence we can reformulate this minimum. So the minimum here applies to the f of xi, but it also applies to the difference of the two. So it's also minimum of this difference. And hence, because each single one satisfies this inequality, we can change it to be Vi. So it's a minimum over Vi. And minimum over Vi is just by definition Vf star. Yes.
So would that be an equality then, not an inequality? The min f of xi minus f star?
Sorry, yeah.
Okay.
Sorry, yes, you're right. Yes. So the importance of this lemma is to connect these two quantities, connect this value gap, this automatic gap, with this quantity Vk star. Vk star, remember, is the maximum distance of maximum radius of a ball, and this is the one we want to show we care about in optimization. So once you have an upper bound on this quantity Vk star, then you can upper bound the function value gap, so you can have a convergence rate. Right, so the next step is, so previously what we described is for general sequence of points x0 to xk, but we didn't specify which algorithm we are using. And later on, we are going to use the subgradient method in particular to generate these points x0 to xk. And we want to show by subgradient method, this quantity is really small. It's as small as 1 over square root of k. And hence we have a convergence rate on this one as 1 over square root of k. As we saw here, the length of the subgradient is not very important. What's important here is one after normalization. It's just the direction. So here we present a version of the subgradient method with the normalized subgradient. Sorry, here should be normalized. So the algorithm looks pretty much like what we had for the gradient, but we just replace the gradient information here. We replace gradient by the normalized subgradient. And here we are still interested in optimization over a set, closed convex set Q. So we also need to do a projection onto Q.
Do you have any specific trick for choosing the subgradient or choosing anyone?
Anyone. You just need to, as we mentioned before, the subgradient is not unique, but every time when you call the oracle, it should be the same one.
Is there any once say we have a set of subgradient, but some subgradient works better than?
In theory, there's no difference, but in practice, yeah, some subgradient may make a difference.
So can I just choose like 0 as subgradient if subgradient is inside, 0 is inside side?
0 will not make your point move. That doesn't change anything.
Then
Yeah, something.
it's optimal, right?
Oh, as we mentioned here, when we define this quantity VF, we want the point. So we want this is along the direction that subgradient is non-zero.
Oh, okay.
By definition, we avoid that. So we make the same assumption as before. The function f is convex and the ambiguity is continuous on the ball, and this ball now is centered at the global minimum x star. And then we can show that the subgradient method satisfies the. So basically, this is an upper bound that we are looking for on the primal gap. Here we need to use an inequality about the projection. That is a question in problem 2. And again, we define Rk to be the difference between xk and x star. As before, we expand this quadratic term. this inequality is just by applying the result here, which is a homework problem. And hence expanding this out and using the RK, definition of RK, we have this is RK squared minus 2HK.
So in the first line, the parentheses should be closed.
Yes. Yeah. So this is just by the definition of VK we defined before. And hence, you can see this is a recursive formula. We again have RK plus 1 square and RK square. So summing this up from, so we're summing from for we replace the K by I and then summing for all these I's. Okay, so summing them up, we arrive at this inequality, and hence we can throw the RK square away, and also by the definition of VK minus 1 star, it's the minimum for all the VI, so we can factor out the V, and this is the final bound. Okay. Now, as you can see, we do have this one shows up, right? We have the VK star, VK minus 1 star here. Over here. So now we have VK minus 1 star less than or equal to. This R0 again is x0 minus x star, and it's upper bounded by R, the radius R. So we can replace this one by R squared. Right. And the rest of the proof is just by applying the lemma we had just now. So this difference is bounded by m times this VK minus 1 star, and hence it's bounded by m times the whole thing, which is a conclusion. So we just apply the lemma. Here it's just by writing the whole thing by this summation of HI.
Why the small r0 becomes the capital R?
Because R0 is x0 minus x star, and it's bounded by this R.
Oh, I'm sorry.
Yeah, it's the initial condition. So far we state the result for general subsize rule HK. Let's see how the result will become when we specify HK. We have two subset rules. One is for first case, let's fix the number of iterations. Let's call it capital K. And in this case, for every hk, we choose it to be R over capital K. You can check with this particular choice, hk constant subsize hk. Do the calculation on the right hand side, you will arrive at this upper bound. So this shows that the convergence rate is indeed 1 over square root of capital K. And this is again a sublinear convergence rate. Second subsize choice is for case when a solution accuracy epsilon is given, then we choose hk to be epsilon over m. M is the Lipschitz constant of the function. And in this case, you can do the calculation over there. This will give you the, so it's the same quantity minus f star. Okay, so with this, so the solution is like this. You have two error terms. One is a fixed 1 epsilon over 2. The other is mr squared over 2 epsilon k. So this part can be driven smaller and smaller when you make k larger and larger. If you use large subsize, this can be very small. It can go to zero. But this one will be remain here. This one cannot be driven to be zero. But our goal is to find an epsilon solution. So if you want to find the epsilon solution, then you do the calculation, move it to here, and then this gives us the k. So if k, so basically it shows that k is on this order. There should be a there should be a square. There should be a square. It should be m squared. So you can show the complexity bound to find an epsilon solution is this much. And for this one, if you want to find an epsilon solution, this also gives you the same complexity. right? So indeed, it shows that these two choices of step sizes, if you want to find the epsilon solution, they will give you the same complexity. So it makes sense. Same algorithm give you same complexity. And in some sense, these two subsizes are equivalent. What we just described is a normalized version of the subgradient method, where we only care about the direction of the subgradient. But there's also another variant with a normalized subgradient. So just take subgradient direction, not normalize it, and it has similar convergence guarantee. So let's look at a particular case with a specific choice of step size, HK. This is called Polyak step size. So suppose we know F star. In some cases, we do know F star. For example, in some optimization problem, we know the optimal function value is just 0. We are solving maybe some regression problem. Regression problem. This is just 0, but you don't know the optimal solution. So you know the function value, the optimal value, but you don't know the solution. Just look for the solution by using the algorithm. And make the same assumption of f as before. F is convex and the Lipschitz continuous over a ball. And if you choose this particular subsize, this is the Polyak subsize, f of xk minus f star divided by the norm square of the subgradient. Then we can have a similar convergence guarantee as before. It's also at the rate of 1 over square root of k. So we again like RK to be the norm of the difference xk minus x star. And then do the same calculation as before. Expand the square term of RK plus 1, we arrive at this inequality. And hence, by using the subgradient inequality, so just the upper bound, this negative term here, negative in product, we have RK square minus 2HK And now let's use the polyaccept size. Just plug in this HK. So this gives us RK plus 1 squared. So this shows that RK plus 1 is less than or equal to RK, so it's decreasing. Oh, by the way, so what we cannot show in non-small optimization by using subgradient method is the function value does not decrease by one iteration of the method. But this distance, RK plus 1 or RK, it does decrease. Right, so we have this inequality. It's out, so out RK, they are always bounded by this R. So it means the iterate is always in this bar. So this means that all the iterates are in the ball. And hence the function f is continuous, which is continuous at this point. And hence, so there is a lemma saying that, loosely speaking, there's a lemma saying that if a function is Lipschitz continuous, then the subgradient is bounded by M. There's a more rigorous discussion on this one, for example, in the book by Amir Beck. This is theorem 3.61. In Amir Beck's book, there's a more rigorous discussion on this one. So this shows that f is Lipschitz continuous in the ball, and also it's also Lipschitz continuous around this point. So loosely speaking, we can say that this is bounded by M. So with this inequality, we can continue upper bounding this one. And now we have another recursive formula on RK, and then we just sum them up. Okay, so from here we just rearrange the terms, so we get this inequality. And for the upper bound, this is just by the definition. R0 is no more than, the initial condition R0 is no more than capital R. And for this inequality, we are just picking the minimum among all the possible i's. So this is multiplied with a k. You have in total k number of them, right? This is I from 0 to k minus 1. And then we just divide everything by k and take the square root. So we have the final result. It's again 1 over square root of k. Any questions?
This subgradient is always bounded, or you need it to be bounded over a context?
Yeah, that's a good point. So in the lemma, it shows that this is always bounded in the interior of the set. On the boundary, it will be problematic in some cases.
Okay.
Well, if you assume f is Lipschitz continuous in the whole space Rn, then this is bounded everywhere. But if f is just Lipschitz continuous on the bounded set, then this is just bounded on in the interior of the domain. So there is a tricky point, but here, just loosely speaking, we ignore the domain. So with this convergence rate result, we conclude the subgradient method. But what we talk about is just one special case of the normalized subgradient with a specific subsize rule. That's the Pollack subsize rule. There are some two other subsize rules, just like the HK we mentioned for the normalized ones. And these are left as homework problems. But the proof technique is quite similar. So it won't be difficult. You can just follow this proof and just change the subsize rule, and you can still obtain similar convergence rate as 1 over square root of k. So now let's move on to a generalization of the subgradient method, which is more powerful in practice. That's called the mirror descent. We will give some concrete examples how mirror descent is connected to some algorithms for online learning. Follow the regularized leader, FTRL, how they are connected to each other. And mirror descent is also powerful for handling different geometry of your problem. Suppose you are not working with Euclidean distance. So it's more practical than subgradient. Subgradient is more like a conceptual version of it, but more practical one will be the mirror descent. This method was proposed by Nemirovsky in 1976 or 77 book. So before we introduce the algorithm, let's first take a detour in the convex analysis. Let's first talk about some notion called convex conjugate. This will be very useful in the analysis of a mirror descent. here this f function is just some real valued function. It doesn't have to be convex. And this f star is called the convex conjugate of the function f. Or in some cases, it's also called the ventral conjugate. So this is just another name.
The inner product is over C, not R anymore. Or
Here, let's assume it's just in R. Here are some properties of the function f star. Suppose f is a closed and a convex function. So closed means remember when we define a convex function, there is a way to define a function is convex from the perspective that a set is convex. That is by using the notion of epigraph. Suppose this is your function f, and I'm looking at this set. If the set is, the epigraph is convex, it's a convex set, then the function is convex. So closeness is by the same definition. If the set, the epigraph is closed, then the function is also closed. Suppose f is a closed convex function, then for any 2 points x and y, TFAE means the following as equivalent. So the 3 statements are equivalent. Inner product x and y is the same as the sum of the 2 functions, f and its conjugate. It's equivalent to either of the 2. Y is in the subdifferential of f, x is in the subdifferential of the conjugate of y. Remember, partial f is a subdifferential. It basically means a collection of subgradients. So here it means y is like a subgradient for f, and x is also the subgradient for the dual function, the conjugate function f star. So from here we can see that the function, the point x and the subgradient, in some sense, they are dual to each other, right? So, and also in their inner product sense, so this is like the primal vector, this is a dual, prime and dual are taken inner product, right? So they are dual to each other. But we are just going to state the result here without any proof. The proof can be easily found in, for example, Mirbeck's book. This is some well-known results in convex analysis. So more clearly, with the same assumption, we can describe what are the two subdifferentials. So what are the collection of subgradients, how subgradient look like. Here we are saying that y is in the subdifferential of f at point x. And here we make it clear. This is a collection of some optimal solutions. The optimal solution is the y that solves this one, right? This y tilde is a solution to this one. Here the little, we don't have arguments. So if you use little a here, little argmin or little a argmax, it means a particular solution. And if you use a capital A, it means a set. It's a collection of all the solution. Because this is a set, so this part should also be a set. So we are taking all the possible solutions. So all these y's tilde, they are subgradients. They're subgradients of function f at the point x. So correspondingly, we also have a descriptive formula for the subdifferential of the conjugate function. So by symmetry, it's also the solutions, the optimal solutions to this optimization problem. But you just interchange x and y. So from here, we can see that if the function f is just closed and convex, the subdifferential set, it's a set, it's not unique, it's not just a gradient. So we do not have smoothness here. This f is just non-smooth. And another thing we can say is that no matter f is convex or non-convex, f star must be convex. That's why it's called a convex conjugate. It's always convex. The reason is that this is a function about x. If you look at the x, the row placed by x, x is only in the inner product term. So this function here is linear in x, right? And we are taking, so this y could be infinite many, but we are taking pointwise function, pointwise maximum for function x. Y can be viewed as an index. For a given y, I can draw a hyperplane for a function x. It's a linear function, right? This is with maybe y1. This is another one, index with y2. When I take the pointwise maximum over x, this one, this is always a convex function in x. Suppose f now is stronger than the one above. F now is closed and strictly convex. Then we can say that this set becomes a singleton. F star, the conjugate function, f star now is differentiable. So you only have one gradient, not subgradient. So then for any y, the gradient of the conjugate function, now this is a little a argmax. So this is just a single one. You only have a unique solution. strictly convex is a little bit stronger than convex, but it's in between convex and strongly convex. For example, we have three definitions for convexity. The first one is by function value. We say the function value of a convex combination for any lambda between 0 and 1, and for any x and y. When this inequality is true, we say it's a convex function. But strict convex just means this inequality becomes strict, right? We just have strict here. So this idea also applies to the other two definitions by first order information or by the Hessian. We just change the less than or equal to or greater than or equal to be strictly less than or strictly greater than. And also for the Hessian, previously we have this Hessian is positive semi-definite. Now just make it positive definite. This is strictly convex. It's because f is strictly convex, so that this optimization problem has a unique solution, so that this one becomes a gradient instead of being a set, being the subdifferential. And also, with strong convexity, we can say something more about the gradient. We can say something about its smoothness. This is a very extremely useful correspondence between strong convexity and smoothness. It's more or less like due to each other, the two notions. Suppose the function f is convex, close and even stronger than strictly convex. Now I can use a parameter to specify how strongly convex or how strictly convex it is. It is parameterized by mu. So when it's mu strongly convex, then we can say the conjugate function is 1 over mu smooth. And on the other hand, you can also say from the other direction, if the function f is L smooth, then the conjugate function is 1 over L strongly convex. So these two are like more or less like due to each other. This notion will be very useful, for example, when we do the smoothing technique. Suppose you have a function that is non-smooth. I do not want to use any non-smooth algorithm to solve for it. I want to first smoothify it and then apply any smooth function, any smooth algorithm. The reason is being that non-smooth algorithm is slower than the smooth one, right? For example, subgradient has this convergence rate, and the gradient method has this convergence rate. And if you use accelerated gradient, it has a much faster convergence rate, right? So if we can smoothify the function first and then apply the best smooth algorithm, we can have a very good convergence result. And this is the way to convexify it by using convex conjugate So suppose this is a nice-smooth function. And first make it, it's a nice-smooth and convex function. I first make it strongly convex by subtracting maybe mu over 2 times the quadratic. So now this f plus mu quadratic, the whole thing as a function, f tilde. This f tilde is strongly convex. So that going through this calculation, so not argmax, just maximize it. Then the f star, the conjugate function, becomes 1 over mu smooth. Now we have a smooth function. So this is a smoothing technique. With that, we can apply, for example, accelerated method on f star. Right. This is a way how to make use of this correspondence between convexity and smoothness, and also how to make use of the convex conjugate.
Is the f double star? The f is off.
Yes, but it's not always true. So the f double star is f when f is, I think it's when it's closed and convex. Convexity, yeah, I need to check the condition, but closeness is always needed. Convexity, I think so, yes. Convexity is needed because f star, this is a conjugate function, so this must be convex, right? An argument here. So when it is f has to be convex. So this holds when f is closed and convex. So this is, I think this is called biconjugate.
One quick question. So, just for, I don't know why you would do this on a smooth function, but say you had a smooth function, you calculate its complex conjugate, it would converge at the same rate as the original function, right? Because the condition number would be the same.
Yeah, but we need to.
It was mu strongly convex and not smooth, I mean.
Yeah, but the mu is something by construction, and also we are applying the smooth algorithm, like for example, the accelerated algorithm onto this function, but not f itself. So there is a difference between f and the f star, and also when you analyze the convergence rate, you also need to take this error into account, f and f star.
Right.
Yeah, we will cover the smoothing technique later on in this class, but this is just to give an idea how this convex analysis notion can be applied. And one thing we need to note that in this case, so for any y, in this case, when the function is strongly convex and smooth, then the gradient of the conjugate function is the same as the inverse of the gradient. Okay, so all these statements are claimed without proof. It can be easily found in any convex analysis book. I think we just have 2 minutes. Let me stop here, but let me do a quick motivation about the mirror descent method. We are again interested in minimizing over a closed convex set Q, but there are some drawbacks in the subgradient method. And f here is again a non-smooth function, just convex, non-smooth, but we may assume Lipschitz continuity of the function. Remember that we just claimed that the convergence rate is something like this. Right. This convergence rate is good in the sense that it's independent of the dimension, right? Well, if it's dependent on the dimension, it's not suitable for large-scale computation. But this one is independent of dimension. But the reason why it's independent of dimension relies on a few facts. So the function f and the set q need to be well-behaved. By that I mean for any point this is bounded by M. This is independent of dimension. And also this R is independent of dimension. They're both just some constant. Well, suppose now you have some function. For example, I want to minimize over a simplex. I want to minimize over a simplex. And I want to minimize over simplex. And also this function is not bounded by L2 norm, the subgradient, but it's bounded by infinity norm. So the maximum component of the absolute value. This is bounded by, for example, constant 1. But this one means that in the worst case, the F2 norm of the subgradient is bounded by square root of n, right? Each component is bounded by n, so the L2 norm is bounded by square root of n. Now this is dependent on the dimension. So if you use this n as a bound m, put square root of n here, the bound will be worse, right? It's not 1 over k, it's square root of n over square root of k. So this will be much worse than this one. And also, so this also relies on, you are using L2 norm, right? This is a Euclidean distance. But what if the geometry is non-Euclidean? For example, if I'm minimizing over simplex, Euclidean distance is not suitable. You may want to use L1 norm. So in that case, this bound is not good. First of all, this is not dependent, dimension-free, and also non-Euclidean distance is not suitable here. So all of these issues will be resolved by using mirror descent, by changing the underlying geometry. We are not going to use L2 norm, we are going to use some non-Euclidean distance. So I think let's stop here and see you on Thursday. Thank you.
这是 L 什么？它是那个gradient system，是那个唯一的。这个病毒，我们需要把这个整。
So as I mentioned in the email, all the lecture notes are available online, and register the course, you can also see the video recording. So you have all the material to catch up, and excuse me. Okay. And also, let's go outside first. And also, the homework will be due in about 9 days. Alright. So you will still have plenty of time. Students. Good morning. Yes. A lot of chalk. I always love these classrooms. They're so close together. No yellow jackets. No yellow jackets. I mean, the last one came out of nowhere. It was like,